My name is Jim Donaldson, as has already been mentioned. I'm going to go through an introduction, a brief introduction, and a video and some observations on the video. And then I'm going to cover a mission overview for Mars and MSL's flight path to Mars. And then I'm going to briefly describe what Avionics does for MSL. As was mentioned, I'm the Avionics Chief Engineer for MSL. And I'm going to talk about some of the challenges associated with processor selection and robustness challenges, and have a brief discussion about where to from here. As already been mentioned, I was born in India and grew up in India. My parents were medical missionaries there. They gave me a wonderful gift by bringing me up there. Those of you who have visited India or who grew up there know that it's a kaleidoscope of sensory and intellectual stimulation, so it was actually a great place to grow up. I've always been interested in things that are electronic and space related. I've also always been interested in how things worked and or didn't work once I took them apart. I sort of had a history growing up of taking in people's equipment to look at it and explore it, and then was unable to get it working again when I tried to return it to them, for which I obviously suffered quite a bit of abuse. My role on the avionics team involved avionics architecture, requirements definition and elaboration, fault tolerance design definition, and investigation of problems and problem reports solutions.
When people look at it, it looks crazy. That's a very natural thing. Sometimes when we look at it, it looks crazy. It is the result of reasoned engineering thought, but it still looks crazy. From the top of the atmosphere down to the surface, it takes us 7 minutes. It takes 14 minutes or so for the signal from the spacecraft to make it to Earth. That's how far Mars is away from us. So when we first get word that we've touched the top of the atmosphere, the vehicle has been alive or dead on the surface for at least 7 minutes.
Entry, descent, and landing, also known as EDL, is referred to as the 7 minutes of terror, because we've got literally 7 minutes to get from the top of the atmosphere to the surface of Mars, going from 13,000 miles an hour to 0 in perfect sequence, perfect choreography, perfect timing, and the computer has to do it all by itself with no help from the ground. If any one thing doesn't work just right, it's game over.
We slam into the atmosphere and develop so much aerodynamic drag. Our heat shield, it heats up and it glows like the surface of the sun. 1,600 degrees.
During entry, the vehicle is not only slowing down violently through the atmosphere, but also we are guiding it like an airplane to be able to land in a very narrow, constrained space. This is one of the biggest challenges that we're facing, and one that we had never attempted on Mars.
Mars is actually really hard to slow down because it has just enough atmosphere that you have to deal with it. Otherwise, it will destroy your spacecraft. On the other hand, it doesn't have enough atmosphere to finish the job. We're still going about 1,000 miles an hour. So at that point, we use a parachute.
The parachute is the largest and strongest supersonic parachute that we've ever built to date. It has to be able to withstand 65,000 pounds of force, even though the parachute itself only weighs about 100 pounds.
When it opens up that fast, it's a neck-snapping 9 Gs.
The At that point, we have to get that heat shield off. It's like a big lens cap blocking our view of the ground to the radar. The radar has to take just the right altitude and velocity measurements at just the right time, or the rest of the landing sequence won't work.
This big, huge parachute that we've got, it'll only slow us down to about 200 miles an hour. And that's not slow enough to land. So we have no choice, but we've got to cut it off and then come down in rockets. Once we turn those rocket motors on, if we don't do something, we're just going to smack right back into the parachute. So the first thing we do is make this really radical divert maneuver. We fly off to the side.
Diverting away from the parachute, killing our horizontal velocity and our vertical velocity, getting the rover moving straight up and down so it can look at the surface with its radar and see where we're going to land. And we head straight down to the bottom of a crater, right beside a 6-kilometer high mountain.
We can't get those rocket engines too close to the ground, because if we were to descend propulsively with our engines all the way to the ground, we would essentially create this massive dust cloud. That dust cloud could then go and land on the rover. It could damage mechanisms and it could damage instruments. So the way we solve that problem is by using the sky crane maneuver.
20 meters above the surface, we have to lower the rover below us on a tether that's 21 feet long, and then gently deposit it on its wheels on the surface.
As the rover touches down and is now on the ground, the descent stage is in a collision course with the rover. We must cut the bridle immediately and fly the descent stage to a safe distance from the rover.
Okay, so now some observations on the videos. Obviously, there were many challenges in several areas. The hardware and software infrastructure challenges were not explicitly described, but obviously existed. They mentioned a 500,000 line of code number. That was actually for the EDL code. The actual vehicle employs about 5 million lines of software code, and the vehicle is obviously very complex and has about 6,000 line items in the parts list for the rover and the spacecraft. The fact that the hardware, the compute platform and software largely go unmentioned is actually a testament to the success of the computing industry in general, and illustration of the Whitehead quote that I had on the first page. Basically, to succeed, obviously, JPL needs the capability to survive environments of launch and space and landing, and this is sort of where the engineering challenge begins and continues on missions in work today at JPL. Here's a history of some of the landers that have been launched, and you can see by looking down this list that about the success rate is only about 50%. I think actually if you look at all the missions that have just gone to Mars, the success rate is lower than 50%. And if you look at some of these pictures, you can see that the configurations for the vehicle are significantly different from vehicle to vehicle, and basically what's going on is a fair amount of what I would consider to be engineering experimentation in terms of what kinds of things will work given certain payloads delivered or attempted to be delivered to the surface of Mars. This is a bigger portrait of the total mission set that have gone to Mars. Here, I'm going to go through these pretty quick because I have a fair number of slides, but most of them are we can just scan through quickly. This Mars Pathfinder and Sojourner, it landed with a balloon system. It was intended to last about a month. I think it lasted 3 or 4 months. These are Mars exploration rovers. It also used a balloon system to land. One of the rovers is still working. I'm going the wrong way. This is a Curiosity rover. This is a picture of the vehicle that's a full-size replica that's used in a vehicle system testbed. It's used to test sequences on the rover before they're sent to Mars to run on the Mars vehicle Curiosity. This is a family portrait for it sort of shows the evolution of the Mars vehicle, and one thing to notice is the huge increase in delivered payload across, starting at 25 kilograms and going up to basically close to 900 kilograms. Phoenix, what the mission was. This is the major picture of the breakdown of the spacecraft for MSL. You can see it sort of has a Russian doll type of configuration where the rover basically nestled inside the other stages that carried it. And basically there's people who sort of look at this and think we had three missions, essentially a cruise mission, a EDL type mission, and a landed mission. There's really 6 different configurations here, electronic configurations that had to be independently tested and verified. These next pictures just show the various stages in construction. This gives you an idea for the size of the rover. This is a person standing next to a heat shield. This is an example of some of the problems that had to be solved. You can see we had issues with parachutes holding up. This particular one was solved by some redesign of the parachute so that it would hold up. There's obviously testing that went on in various configurations, which I'll just flip through very quickly. You can see this sort of documents the construction of the vehicle in preparation for flight. The vehicle getting ready to be put in the fairing, encapsulation at KSC, moving on to the pad, loading it on the Atlas V, and then ultimately launching on November 26, 2011. This brief animation shows the various science complement that's on the vehicle. The vehicle has one of the most capable set of geological science instruments that have been put on Mars. There's some instruments here that are repeats of what went out on MER, but they've actually been improved so their capability is better than what MER had. The ChemCam here attracts a lot of attention because of its laser-induced breakdown spectrometer. This shows a little bit more of the engineering side of the rover. You can see a UHF antenna here. The rover actually has 2 UHF radios. And you can see RTG and RTG power source. This is where the rover gets its energy. The energy is stored in batteries, and the rover actually spends a fair amount of time doing what we call sleeping, which is essentially most of the electronics turned off and the RTG basically sourcing energy and refilling the batteries. So what is avionics? At JPL, this is sort of a squishy or nebulous term, and it's used to describe a combination of C&DH, which is command and data handling, guidance, navigation, and control, and flight software functionality. On MSL, it's specifically referred to a combination of power and pyro functionality, motor control functionality for both hardware and software for the motor control inner loop, and C&DH functionality. And flight software that ran in the main computers was sort of treated as a separate entity. On MSL, this functionality was split across actually several assemblies, and the avionics is mostly redundant, allowing continued operation of the rover in the presence of single failures that affect only one of the each of the redundant pairs. These are the kinds of things that the Avionics does. I won't bore you with all of this, but basically it interfaces with attitude control sensors, with the instruments, and the motor control computers, and all the power subsystem hardware. And it takes lots and lots of analog measurements that are used on board for fault protection and for telemetering to Earth, so that the operators can assess the health of the vehicle. Most of these functions are implemented in a combination of FPGAs and the software that controls and actually runs the FPGAs, and these FPGAs are scattered across the spacecraft. So this is sort of an inside view of, if you pop open the lid of the main body of the rover, which you saw in those earlier pictures, what you would see, and basically you can see that the entire innards of the rover is just packed with electronics and cabling. There's a SAM instrument here. The boxes up here, there's 2 Rover compute element boxes, redundant boxes. This box here is the motor control box that has a Spark processor in it, and there's power assemblies over here, and many the radios and other instruments packed in there. So you can tell that the test and integration activity for this were actually pretty involved. The actual conceptual design of this is fairly straightforward. You can see that the electronics actually was divided into 3 separate stages. Each one of these stages, the inner portion of the Russian doll had to keep working as the other stages were shed. So that when the cruise stage went away, obviously the descent stage had to keep working. And when the descent stage went away, we're left with this ensemble of hardware here that is still on the surface of Mars. And essentially most of the communication between the engineering subsystems is actually on old legacy buses, 1553 buses, with a special 1553 bridge that was used so that we could tolerate the separation event when it happened. And if you look at this, there's computers in the RMCA, the DMCA, which ran the EDL thruster motors. There's computers in each of the electro radios and in the X-band radio, and there's computers in the RCE A and B, which are RAD 750 computers. So this talks about the computers in the avionics. There's actually more computers in the engineering sensors and the ones I mentioned that are in the radios. So you can see that by the standards of this group, this would not be considered high-performance computing. In terms of the standards of the aerospace community and the flight community, we actually are flying the best available rad-hard processor that we could find at the time the design activity was going on. Now this talks about what kinds of factors were important to JPL, and you can see that the attributes that are important to JPL vary depending on who you ask at JPL. Since I work on the engineering on the flight side, you can see that the robustness is high. We're actually looking for power to be low. We want low power so that we can actually get some science done without spending lots of mass on energy sources. And the performance is not as important, and I say to a point. I mean, obviously we need a processor that's capable of doing the kinds of things that we need to do. In the test area, most of these restrictions on power and robustness go away, and actually in the test area you'll see people using a lot higher performance machines, and a bunch of the Monte Carlo simulations that were done for EDL and simulations, aerodynamic sims for the parachutes, I believe were run on the kinds of high performance machines that you folks work with more commonly. And then with the science instruments, because the needs of science vary quite a bit. Some of the science instruments have very short lifetimes. There was a science instrument that was used just during EDL, and once it was ejected, his job was done. So these factors actually become, vary depending on the application of the science instrument. For the engineering side, these are really the biggest factors in the choices that we made. Radiation tolerance is obviously a big deal. I'll briefly just touch on radiation. I won't talk about these other ones because we're somewhat limited in time. The radiation requirement for Mars is actually pretty low. It's only 4 kilorad. There's missions. A mission that I worked on going to Saturn, I actually had a much higher radiation requirement. And we're looking at missions going to Europa, which have much, much higher radiation requirements. The real thing that sort of is a swinger in terms of radiation is the GCI environment and the solar energetic proton environments basically are such that they can still cause upsets in critical electronics, resulting in resets or logical lockup conditions or latch up. So part of the engineering enterprise is actually going through the activity of checking that the parts can tolerate radiation, that they don't latch up destructively. You can imagine if there's destructive latch up, basically the mission would be lost. And further complicating the mission was the fact that the rover actually takes some radiation sources with it. It makes its job even more difficult because of this. And here's just basically the DAN instrument as an example. RTG was another example. There was a bunch of testing done to determine the tolerance of the electronics to high energetic neutrons. After significant testing, it was determined that the results or effects of the highly energetic neutrons were similar to what we would get anyways from the GCR environment. As far as radiation mitigation methodologies, JPL employs a number of different methods. Some of them involve just shielding the victim and basically using shielding that's inherent to the vehicle, or intentionally shielding using location or spot shielding devices to get the TID within acceptable limits. We also buy parts that are intentionally hardened, and that's true with our processor parts. And there's testing to look for some parts are just based on process variations are harder than other parts. So we actually go through a fairly rigorous test program, and parts often fall out and redesign occurs because of that. And then we use circuit design methodologies that to address radiation effects. We use redundancy and automatic error correction. We use fault masking, TMR, and graceful degradation. We use self-checking state machines. We use watchdog timers. The mechanisms to address the radiation threat were basically multi-tiered. The lowest level being memory scrubbing, fault masking, and graceful degradation using EDAC. Further up the chain, we had watchdog timers that actually would reset various components or power cycle various components if the component became unresponsive even after a reset, so that we'd have a chance to try to clear the fault and keep working. And each layer of this fault response hierarchy was put in place to address possible faults derived from a fairly detailed functional failure analysis. These other challenges here were actually fairly significant as well, but I'll just breeze through them. One is the fact that the temperature extremes on Mars are relatively extreme compared to what we see here on Earth, and also because of energy limits and the kinds of lubrications used in motors, actuators had to be turned on to do things in advance of being used so that they would warm up. And this actually caused energy, an issue in terms of the amount of energy availability for science. And so solutions were devised for both of those. The temperature cycling issue was handled via extensive testing of the parts that would see the temperature extremes. And earlier on I mentioned this thing about the rover going to sleep. We also have something on MSL called the dream mode. It basically is functionality that exists in some of the power assemblies that allows the power assembly itself to monitor the health of the vehicle and turn on heaters before it turns on the main compute element, allowing the actuators to be preheated before the main computer comes on, so that when the main computer boots up, the actuators are essentially ready to go and do their job. So this shows the kinds of temperature extremes we're talking about here that had to be designed for. The last issue had to do with all the cable cuts. There was concern at one point about the cable cuts causing signal integrity issues that could lead to resets. We basically spent a lot of time analyzing the cable cuts and looking at the power bus, the bounds in the power bus. And we spent a fair amount of time implementing what was called Second Chance. It was a software build that lived in the redundant compute element that could take over EDL and run EDL if the primary computer actually had a reset. I think, let me go up here, sorry. Okay, so this is a picture of where we landed on Mars, Gale Crater. This is a closer picture of it in Mount Sharp. Mount Sharp rises about 3 miles from the bottom of Gale Crater. This shows the landing ellipses for the MSL vehicle and previous vehicles. You can see that some of these landing ellipses, like for Viking, were just gigantic. And they've been shrinking, and a landing ellipse for Curiosity is shown right here. It's basically 12 by 4 miles. It's still relatively big, but much better than prior missions. This is a picture of Mount Sharp, picture of the rover after it landed, picture of the foothills of Mount Sharp. This little dot that you see here, or don't see there, it's blown up here, is basically it would be about the size of the rover once Curiosity once it gets from its current location over to the foothills of Mount Sharp. This is a picture looking north to the crater rim. This is a picture of the arm of the rover. Another picture of the head on the arm. And this is a picture of the mast of the rover. And this picture and this picture were basically taken by the respective cameras in the two devices of each other. So it's a sort of two two items pointing at each other, taking a picture. This is a picture here. You see these little dots here. These are the result of the ChemCam instrument actually firing its laser. It's about a gigawatt of power across the 5 spots with 50 shots per spot. The instrument actually fires a laser, and then based on the excitation of the material that's ablated or vaporized, it use spectroscopy to do element analysis, I believe. Is there a question? Oh, okay, sorry. This is what some people might wish we were doing, but we aren't. So things are actually safer than they look. And this is a picture. This is actually not intended to be. It's not intended to be a plug for the next Transformers movie. Basically, the point of this is that with the devices that we design at JPL and at other centers of NASA, we basically are building human prosthetic devices, if you want to think of them that way, that extend the reach of humanity across space. And when the rovers on Mars, basically we're on Mars, and we're basically seeing Mars through the eyes of the rover and sensing the world around the rover through the rover's sensors. And this is actually one of the sort of joys of working at a place like JPL. Whitehead actually had a saying that he said, all the world over and at all times there have been practical men absorbed in the irreducible and stubborn facts. All the world over and at all times there have been men of philosophic temperament who have been absorbed in the weaving of general principles. I see the practical and the philosophic, or the engineering and the scientific, as an interesting case study in a virtuous cycle where the tools that we design actually go into making discoveries possible in the scientific realm, and as the scientific discoveries happen and new fields are opened up, the markets for increased innovation happen in the computer world, and the cycle's been going on and has pretty much has been happening continuously now for many years, and is pretty much goes unnoticed by most of the people during their daily lives, including mine. This is my final slide. I have just a little quick story here, folktale from India. You can see that this is not to scale. You can see that JPL is way down here. It's actually a little speck in the electronics world. And there's a folktale from India about, it's called the Eagle and the Myna. And basically, you've heard of the king of the jungle, the lion. Well, the birds of the jungle had a conclave, sort of like what happened at the Vatican, and they were all upset because they had heard that the jungle animals had gotten together and declared a king of the jungle, and this actually generally irritated them, and they said, we've got to have a king of the birds. You know, it's just not fair that there's a king of the jungle and no king of the birds. And so the myna bird, a small bird, said, well, why don't we have a flying contest about who can fly highest? And there was all this talk back and forth, and the eagle said, well, of course I can fly highest, why bother with this contest? And ultimately they decided to go ahead with the contest. Now, some of the birds, like the ones that couldn't fly, like the peacock, were agitated about the fact that the contest didn't include them. But anyways, they had the contest, and they lined up, and a bird chirped and they all flew up into the sky, and just as they flew up, the mynah bird actually grabbed a lift on the eagle's back, and up they went, and the eagle got way above all the other birds, and he said, okay, it's pretty clear I won this contest. And just as he starts to dip down, the mynah bird flutters above him and goes higher, and all the other birds who are looking up, start, sort of a raucous cawing and making noises. And ultimately the mynah bird got declared to be the king of the birds, and not the eagle. And essentially the point of the story is that even if you're small, sometimes you can see further if you're basically riding on the backs of eagles, which is essentially what JPL and other institutions do when they use high performance computing. Thank you very much.